Presolving. Let's do some more math again. Arguably, one of the most important parts of each MIP solver, trying to do as much good to your model as you can before you even start fully solving it. So the majority for this presentation will be about that pre-solving. Towards the end, I will say something about, well, loosely related procedures or more MIP procedures that I didn't want to talk for a full 45 minutes or didn't have the time to, but still would like to mention to you: conflict analysis and restart. So this is what's going to be covered in this presentation. Domain propagation, the small sibling of pre-solving, as mentioned before. Some of the procedures that we see here will be applied in domain propagation. Many of them will only be applied in pre-solving. Globally, domain propagation is what you do locally inside the tree search. Pre-solving. So we start with linear pre-solving, which you would also apply to LPs and in the same and similar way to MIPS as well. Goal here: reduce the problem size if you can, try to find variable fixing, get rid of redundant constraints and so on. For obvious reasons, smaller problem means smaller solution time. The linear algebra in your simplex will be, your decompositions will be faster and smaller, and really literally every loop ever in your problem that loops over rows and columns will be faster when you are having less rows and columns. Other goal is improving the numerics of the problem. For example, by scaling, this will come as an unexpected extra in the machine learning talk on Monday. I won't cover scaling today. One thing, if you are really doing linear pre-solving for LPs only, you want to keep the ability to post-solve both primal and dual solutions. So post-solving means after you have applied pre-solving, you got like a reduction of your previous and maybe a reformulation of your original problem. You find a solution for this one, but the user, the modeler, is not interested in what new problem you are now actually solving. They need a solution for their original problem. So you need to be able to undo all the changes in a sense and deliver them a solution in the space that they have formulated the problem in. That's something that you need to keep in mind. And also you want to preserve duality for LPs. So in if you post-solve the solution, you want to get a primal dual solution pair that matches each other. Not as trivial as it sounds if you're doing funky, fancy stuff in pre-solving. I would like to, or we need to distinguish two different types of pre-solving reductions. Primal reductions, those are based on feasibility reasoning. You can argue that in whatever feasible solution you find for your problem, a certain value will never be possible, so you can exclude it from the domain. That's like a prototype of a primal reduction. No feasible solution gets ever cut off. And dual reductions, that was the thing with the zero objective heuristic. Those take the objective into account and do arguments like, well, there might be feasible solutions with that value, but I still can do a reduction because I know that when I apply this reduction, there will be at least one optimal solution left in the problem. So I'm excluding something which is redundant for the question that I'm trying to solve. The task of a MIP solve or LP solve is to find one optimal solution. I'm free to throw away suboptimal solutions. I'm free to throw away optimal solutions as long as I keep at least one optimal solution. Sounds like a super fancy thing, but think about a free variable, a variable that does not occur in any constraint. 0, 1 variable. Well, obviously, if I fix it to one of the two values, it doesn't matter for the remaining problem. but I will throw away a potential optimal solution if it doesn't have an objective value. Okay, and then there's MIP Solving, and this is where things get interesting, because now as an additional most powerful tool, you have integrality that you can exploit to strengthen AP relaxation, to reduce the search space. Trivial example picture here, if you have a integer variable with a fractional bound, well, round that bound. You will see some more fancy stuff later. Also, in MIP Solving is where you identify substructures. This is not as much done for AP Solving, like all those league tables, those multi-commodity flow networks that we've talked about. These would typically be detected during pre-solving to be ready when the solver starts. Connected components, more often than you would believe in practice, you see that people give models to a solver which consist of completely independent submodels. So there's no interaction between, say, the x variables and the y variables. They don't appear in a common constraint. So you could solve these two problems individually, but you need to detect that. It's trivial to detect, but you still need to do that. Otherwise, if you interleavingly branch between those two problems, that's exactly the combinatorial explosion that you wouldn't want to have. Okay, good news is for MIP Solving, you don't need to preserve duality. Why is that? Because there's not really such a thing as duality relationship in MIP. So you only need to be able to post-solve primal solutions. That makes things much more easier. The examples I gave so far were all trivial, and that's where pre-solving starts. The trivial stuff, somebody's got to do it. You could see this as an argument between the solver developers and the modeler. So I would claim a modeler should not put such things into a model. A modeler would say, well, a solver should be easily be capable of detecting these things. So at one point we surrendered. All of this is implemented and really trivial. Remove empty rows, columns, tighten fractional bounds of integer variables, substitute variables that have been fixed to a certain value or aggregated. One variable equals another variable, maybe times some coefficients and plus some offset. Just exchange this. Bound shifting of general integer variables. 5 lines of code when I implemented this in Skip a couple of times ago, 2-3% speed up within an hour of work time. Convert variables that have bounds like 4 and 5 to binary variables, and suddenly all your procedures for that only are implemented for binaries. You might see this as a shortcoming of the implementation of the rest of the code, but will be enabled. Replace singleton rows, like if a row is essentially just a bound. Normalize constraints. This goes into the direction of scaling, but in particular, if you're having, if all your coefficients are integral, they have a common multiple, might be a good idea to just divide by the greatest common divisor. Classify constraints. So which of your constraints are knapsack constraints, for example, to be applied or to be used for knapsack cover cuts before, or might be easily reformulated as knapsack constraints by complementing some variables, exchanging some variables. Try to find these type of things. So yeah, I mean, I was trying to blame this on the modeler. Truth is that in 99% of the cases, I mean, there's behind a particular MIP, there's not a modeler modeling that one problem and giving it to a solver. There's a general model in which data gets fed, they are automatically generated and contain a lot of artifacts, things that might be non-zero the one day, are zero the other day, and thereby create some empty constraints, some redundant columns, whatnot. And again, the first modeling attempt, more often than not, is wrong. Pre-solving is great at spotting these errors that you made where you accidentally casted your problem in feasible. We typically then tell you something in the log like the problem is feasible because of row XYZ. You look up row XYZ in your model formulation and say, oh, oopsie. Yeah, so you want to recognize this quickly. Again, if a software cannot recognize trivial things, it does not look trustworthy. So another good reason to have all of these things. And often also these trivial reductions result from prior non-trivial reductions that you did. I'm really stressing this because there's some other communities where essentially such a thing as pre-solving is like, well, that's not interesting. We don't really do this in our solvers. Not like in mathematical optimization, but yeah, I don't want to point fingers here, but it's important to have this in mind. Okay, we have a working example for the next 4 slides. So this is, well, in a sense, it's 2 inequalities, but they change the same linear expression here. So I just put this as like one constraint, which has both a lower and the upper bound. If you wish, reformulate this as 2 independent inequalities. You saw this on the first day, no big deal. I would like to have one of the variables binary, the other one should be a little bit general integer, like 0, 1, 2 as feasible domain. If I draw this here, this is that heptagon, no, pentagon, sorry, a pentagon. Here, that's the feasible region, the dark blue point, that's the linear feasible region. Just for curiosity, I marked the 2 feasible integer solutions in there. So these are the 2 sides of the constraint. Just maybe spend a couple of seconds to think about what could you reduce that formulation, or maybe even without looking at the picture. What could you reduce this to? You can, sorry? X2 to 2 and yeah. So you can exclude one value from the domain. That's what you mean, right? Yeah, correct. It's more like an open-minded question here. I don't want to discuss or see the full solution. I'm claiming it's not that trivial to see the full power of what you can do here. Let's go forward and look into linear pre-solving. And we will use this as a working example and see what we can come up with in the end. Okay, so an important concept and known for almost 50 years now is using minimal and maximal activities. And I think, Marco, can we claim that there's a sign error in this original paper? I think in the one lecture that we did together, we proved that somewhere in this paper there's a sign error. Anyhow, so what is this about? So we look at the linear constraints, we look at the bounds for all of the variables, and we define something, namely the minimal activity of this constraint, which is the minimal value that I can get over the variable domain. Very easy to compute. Everything that has a positive coefficient goes in with its lower bound. Everything that's a negative coefficient goes in with its upper bound. So for our working example here, the minimal activity would be 0. Both positive coefficients are positive, 0, 0, and these are like the 2 different bounds on the constraint. Okay, you can do the same thing for the maximal activity. And the first observation that I can do, well, if the maximal activity, which is here, I think 6, right? 1 times 2 plus 2 times 2 is 6. If this was smaller or equal to the right-hand side of the constraint, it's not for our working example, then the constraint would be redundant. Like if the upper bound was 7 here, for example, we could just throw the constraint away. If the minimal activity was larger than the upper bound of the right-hand side of the constraints. Again, it isn't in our working example, but if it was, the whole problem is proven to be infeasible in pre-solving. Okay, so far so good, the trivial stuff. The next observation is I can use this to derive new bounds on the variable. Here comes your 2 being excluded. So let's just do this now for the positive coefficients. Again, all of this equally follows for negative coefficients or for different signs of the comparison sign here. So we're adding a 0 here, and then we're bringing all the stuff to the right-hand side to derive a bound on x1. And then we're doing some estimates here. So this formulation here, which is just the original plus this x1 once added and subtracted out again, is equivalent to x1 being less than the right-hand side minus this term and divided by the coefficient. And I can do an overestimate of this term here by using the minimal activity and plugging in the lower bound for the variable that I'm currently looking at. Okay, this is really useful. Let's look at our example. So here we have x2 is less or equal than the right-hand side minus the minimal activity, which was 0, minus 2 times the lower bound of x2, which is also 0, divided by the coefficient 2. That's 1. So indeed, we can exclude 2 from the domain of the variable. So that's bound strengthening. If I get for an integer variable, if I get a fractionality somewhere along the way, I can apply rounding. You see, this even works for would even work for continuous variables, or does work for continuous variables. We didn't use inequality in the argument that we just made. Okay, so in our picture, this would essentially reduce this problem to this problem. Good. Third observation, coefficient tightening. So again, we're looking at the case where AI is greater 0. This procedure is defined for binary variables. Oh, luckily, we just made both of them binary. And we need or this only gives us something, works when we find a variable where once we subtract the coefficient of the variable from the max activity, this is smaller than the right-hand side of the constraint. So this means that this variable alone can push the constraint over the right-hand side or not. If this is strictly smaller, essentially what we can deduce from here, if this is strictly smaller, then this value was too larger than it needed to be. Okay, sorry. So the claim is we can reformulate this in that way. And again, as for the other disjunctive arguments we saw before, you can just plug in 1 and 0 to see that in both cases, this reformulation is valid and holds. Okay, so with that in mind, let's rather look at the example and see what happens. We start with x2 again, which now after our first bound strengthening reduction is a binary variable. And indeed, the maximum activity is now, that's now 4. So 2 times 1 plus 2 times 1. And 4 minus 2 is strictly less than 3. So we should be able to tighten some coefficients here. Okay, so we apply the formula that we see here, and we solve this. And what we get is this new constraint. So we reduce that constraint to that constraint. It's removing part of the linear relaxation. It's keeping all integer solutions feasible. We did a disjunctive integer argument here. And the same thing we can do for the other coefficient, x1. And then we will suddenly end up with, well, for the integer solutions, x1 plus x2 less or equal 1 is keeps the same set of integer feasible solutions than 2x1 plus 2x2 less equal 3. We can do the same thing for the other half of our working example here. So for this part of the constraint, and then we will suddenly get x1 plus x2 equals 1. We could still work with that. It would have the same set of feasible solutions. And because this is connecting two variables in a single constraint, this is an aggregation of variables. We can just eliminate one of the variables. So this whole thing in the beginning with general integer variables completely collapses into one variable, into one point in pre-solving. Not that trivial to see, I claim, from the point where we started from. Okay, dual reductions. So, dual reductions, well, they need to ensure that you keep at least one optimal solution. As said earlier, the trivial example, fixing variables that appear in no constraints. Dual fixings. If a variable appears in no equation, only with non-negative coefficients in less equal constraints, and only with non-positive coefficients in greater equal constraints, and it has a non-negative objective, that's a lot to ask, I admit, then it can be fixed to its lower bound. With our prior knowledge, I could have reformulated this as if the variable has 0 logs in one direction. There's a direction with 0 logs, and this is the good direction from the point of the objective. So this is the direction in which you minimize the objective, assuming a minimization problem. Then you can fix that variable to that lower bound. Assume this case here. So this should be like a variable. This should be the lower bound here of the y variable. Those are all the constraints. This is the direction in which we want to minimize. In this direction, our variable is only constrained from above. And the good direction from the sense of the objective is going down. Well, we can fix y to 0 here. All the optimal solutions are on that line. Well, for that particular, if that's the whole MIP, there's only one optimal solution. But we could, prior to throwing a simplex algorithm, fix this variable to 0. That's dual fixing. Fixed to 0. Dual aggregation. Similar. Except, well, if there's only one constraint which violates all of these statements here, we cannot fix the variable, but we can essentially aggregate the variable to derive its value from that constraint. And yeah, dual bound reduction, it's a bit more involved. Let's skip. Probing, mentioned in the context of branching. It's also a procedure that's explicitly applied during pre-solving. Strong branching without NLP. So fix binary variables to 0, to 1. Do your bound strengthening procedure that we showed before. That's essentially the essence of dominant propagation, this bound strengthening, which we use for our working example, this first step there. It still can be expensive if you do this for all variables. So it's typically only applied for a subset. This makes the sequence dependent. There's different working limits. Again, a lot that an engineer can tweak. And what do you get from that? I mean, you don't want to branch now, so what else is there that you get? Well, if you find that from fixing a certain variable to 0, and the remaining problem is infeasible, and fixing it to 1, and again the remaining problem is infeasible, then the whole problem is infeasible. Simplest disjunctive argument that you can think about. If only for one of the bounds you get an infeasibility, you can fix the variable to the other bound. If from fixing the variable to 0, you get a certain fixing for another variable x2. It doesn't need to be binary. It could be like a general integer or even continuous variable. And fixing x1 to 1, again, by propagation, by bound strengthening, gives you a fixing of the same variable to a different value. Then you can express x2 in terms of x1. So if x1 is 0, then this formula here will be a, obviously, so this cancels out, it's only a. If x1 is 1, you have a plus b minus a, it's b. Independent of like how many constraints or so these variables. Here you can express one in terms of the other by that logic that you derive from probing. If fixing a variable gives you only a bound on a variable, fixing the same variable to 1 instead of 0 gives you a different bound or even the same bound, it's safe to apply the maximum of the two as an upper bound to that second variable. Oh, there's even more. If fixing it only gives you something on one side, you can at least remember that information. If I am able to fix that variable again, I do get something from that. That's what you use the so-called implication graph for, and that you can use for heuristics, for lifting, for branching, you name it. Okay, finally, maybe not finally, but multi-row and multi-column reductions. There are things that are called parallel rows. So if two rows are exactly the same, then you can eliminate one of them, obviously. If they are parallel to each other, if they have a different right-hand side, you just use the one with the stronger right-hand side. If you have two columns that are parallel to each other, you can join them into one column, into one variable, and extend the domain accordingly. You can do the same if there's only a domination relation, or a similar thing if there's only a domination relationship between two rows. So if one row is in all the coefficients only stronger or only weaker than the other row, like think of two columns that are parallel, but one of them has a larger coefficient in the knapsack constraint, for example, then you would prefer to use the one which is less restrictive in every solution over the other one. So you would only use the second variable when the third variable, the first variable has only been set. So you can deduce something in that case. I think that's the one message. And the other thing is, well, this is with some clever procedures. This can be done in linear time. This is a quadratic algorithm. Don't do this fully. You apply heuristics to detect dominated rows and columns. There's sparsification. So find ways how you can add one constraint to another constraint to get eliminations. And then there's clique merging, like something that you can deduce from your clique graph or your clique table. If you find individual cliques that all together imply larger cliques, it's like you have all of these three constraints in your matrix as like native original constraints. You can simply replace it by one big clique constraint. And more. Implied integer detection mentioned somewhere yesterday. So there's an equation where, or even also in some cases an inequality, if you use duality arguments, where all variables in there are integer except for one. Then for an equation, necessarily it also needs to be integer if the coefficients are integer. For an inequality, you might be able to do a duality argument. GCD reduction, you can divide constraints by their GCD and then do, again, some rounding argument. I mentioned disconnected components. So here's now how you detect them by applying a depth-first search on a graph that corresponds to your matrix, and then solve individual components. If they are small, you can just solve them away in pre-solving. If a problem decomposes in equally sized components, you need to handle this in a branch and bound search. Again, something with analytic centers. So an analytic center, as I said, the center of gravity at least for your imagination. If the center of gravity of a polyhedron is at one of its bounds, then it's because this polyhedron does not extend in that dimension. That's the geometric hand-wavy argument. So if this might only be implied by a large set of constraints, but if you compute the analytic center and you see that it's at one of the variable bounds, then you can rightfully fix it to that bound. Configuration pre-solving. Maybe in the interest of your lunch, let's skip over this. And let me mention reduced cost fixing. And I just remembered that we still need to talk about conflict analysis past lunch today. So reduced cost fixing. That's more of a domain propagation kind of thing. So you consider the reduced cost of an LP that you solved, and those reduced costs gives you an underestimator by how much the AP value would change if you shifted the solution towards the other bound. So reduced costs you have for non-basic variables that currently sit at their bound. So, and the reduced cost says essentially, if you left that bound, what would this cost you? So in the picture, the reduced cost is something like that value here. It's an underestimator because the real value is larger. And if you compare this against the incumbent solution value, the primal bound that you have, and you see that for, well, let's start with a binary variable that's at 0. If adding the current LP value plus the reduced cost for bringing it to 1 is larger than the objective of the incumbent, then you can again rightfully fix that variable to 0. Because you can never get a solution that's better than the incumbent with it. Same argument for general integers. If it sits at non-zero bounds, you're just getting some additional coefficients into your argument. Even for continuous variables, you can do bound reductions here. You can do this locally after every AP essentially that you solved. The global reduced cost from your initial AP or from every other global AP that you solve, like doing your 20 rounds of cuts, you solve 20 APs, you can store the strongest reduced costs that you found. Keep them in mind. Maybe they don't give you a reduction at this point because you haven't even found an incumbent solution yet. But if you find an incumbent solution later in the search, you can still do the very same argument and fix that variable or change that bound globally. Let's quiz a bit and then try to do conflict analysis in 5 minutes. Let's check whether you paid attention. Quiz time. First question, pre-solving. See, yeah, great stuff. It may cut off optimal solutions. I said that often enough that people remembered. Okay, bit more tricky. The maximum activity of this is excellent. Yeah, it's 5. And what is not the goal, not one of the goals of pre-solving? Yeah, that's what we have heuristics for. Okay, conflict analysis. Let's ride through this. Motivation. Half of the nodes in a binary branch and bound tree are pruned in the end. Like half of the nodes in a binary tree are leaf nodes, as you know. For many different reasons. That might be because they're infeasible, because they're bound exceeding, and so on. The idea of conflict analysis is to try to learn what led to that infeasibility, generate valid constraints from this to cut off other parts of the tree and use it for propagation. There's 2 main sources of infeasibility. Either you can detect infeasibility in propagation. In a sense, that's the good case because it's easier to explain one, or you can get it from infeasible LPs, and then you can get essentially do a heuristic argument to backtrack to withdraw to the first case. Okay, this idea comes from the subsolving community, where you all your constraints takes these form of clauses, literals, x that are either x or the negation of x, or binary variables, and you want to find an assignment that fulfills all of your clauses. There's no such thing as an objective. It's easy, very easy to reformulate as a binary MIP. Like, for example, if this was the clause here, then this would be the MIP reformulation of that. So you're summing up all of the positive letter weights, you're getting a minus coefficient for the negative letter weights, and then you need to do something about your right-hand side. So it's 1 minus the number of negative letter weights. Easy to check out, just believe me for the moment. Okay, the working horse in subsolving is unit propagation. So they don't do branch and bound. They don't have or can't make good use of relaxations. They do branch and propagate. And the only propagation that you can do is when all but one literal is fixed. Then you can fix the last literal. If all but one are fixed to the bad case, to the zero case, so to say. Like, for example, here, if x is 0, x1 is 1, and x9 is 0, then the last remaining literal x10 must be equal 1. That must be true. Okay, so I can represent that logic here of I took these 3 fixings and derived another fixing from that in such a tiny graph structure. So having x7 at the positive value, x6 at the 0 value, at the negated value, x9 at the negated false value leads to x10 taking the true value. Okay. If I do this for all the propagations that I did during my search, so the green nodes here are my branching decisions. So in my first branch, I decided I want to branch x1 equals false, x1 equals 0. That led to x2 being fixed to 1 and to x3 being fixed to 0. Then I was done with unit propagation. I branched on x4 equals true equals 1. That led to x, that together with the knowledge of the bound of x2 led to x5 equals 0, and so on and so forth. Yeah, I think you're getting the idea of what happens in that graph. This is the constraint that we just saw, the propagation that we just saw. And at one point, I do a propagation that leads me to an infeasibility, to a contradiction. So like I have this clause here in my set of clauses, x13 or not x14 or not x15. And by previous propagations, I fixed all of them to the wrong value, so to say. I fixed x13 to 0, x14 to 1, and x15 to 1. So then this clause tells me this cannot be, this is infeasible. Okay, so far so good. That's the conflict graph and the conflict analysis sense. And the crucial observation now is that each cut in that graph, and I'm not talking about cuts not in the MIP sense, but in a graph theoretical sense, a cut through a graph, a set of edges that separates one part of the graph from the other. Each cut in the graph gives rise to a valid constraint for your original problem. Like this one here is hopefully the one that's there on the right, or is it? So x12, it features x12, x7, x6 that goes over here, and x8. I think that's all the nodes that are directly to the left-hand side of the cut, from which there's an arc leaving or crossing the cut. So this is a valid constraint for the original problem then, because it's exactly the opposite statement of all these propagations. It says one of these propagations needs to be done, one of these bound changes needs to be done in a different way, because how they were done ultimately led to infeasibility. Okay, there's a couple of trivial cuts in there. What's called the lambda cut. We don't really need that because we already have that constraint in our set of constraints, and the so-called no-good decision card, which has all our branching decisions. Well, at least if we do not restart our search, this is a correct statement, but we won't use it because we already just explored that part of the search tree. But everything in between, and there's again heuristics for that, how you find a good card in that graph to get a promising conflict that you might add, is what you can get from this infeasibility. Okay, so far for the MIP part, for the SAT part, that's the logic. It's there's technical details, but it's relatively straightforward to generalize this to MIP solving. So first of all, you need to be able to work with general bounds. The logic is really the same. Yeah? There's nothing new in there, just the constraints that you get from it are of a bit more general type because they're not logic clauses, but they have like, again, different bounds in them. And then the crucial bit is that the infeasibility often is not detected by the LP, by propagation, but by the LP. What you can do there is to derive an initial reason for the infeasibility from your infeasibility proof. The infeasibility proof is the dual array. The dual array combines constraints and bounds into a proof of infeasibility. For your conflict analysis, you only need to consider those bounds that had a non-zero value because those are the only ones that were involved in the proof of infeasibility that you derive from the LP. And you can then again sparsify this a little bit beforehand. There's a lot of different points in time where you can start conflict analysis everywhere where you solve an LP, and these are many places. As you see here, I'm skipping over that. And I'm finally mentioning restarts within 1 minute. Again, something that the MIP community learned from the SAT community to periodically restart your solve. Again, for the main motivation in MIP here is to apply more pre-solving reductions. If you found a lot of reductions during your root node processing, for example. So for example, from your reduced cost fixing, that's one of the biggest triggers for restarts. And again, a heuristic question of what is a good point to restart. Traditionally, solvers only did this at the root nodes when a certain percentage of variables have been fixed, or when the objective falls out of the problem, suddenly you're only viewing a feasibility problem. And rather recently, there has been this, and a couple of follow-up papers which look at restarts during the tree search, which the SAT community has been doing for ages. And finally, the MIP community found good ways to integrate this into their solvers. Some solvers have had that for years and never told the rest of the world. Let's do one final quiz before Thorsten gets his picture. Okay. Anyone have an idea for the first one? Maybe no. It's so the logic of a conflict constraint is that you say at least one of these bounds has to be set in any feasible solution. Oh, whoops. Any idea for the second question? So yeah, the conflict analysis for infeasible LPs uses the dual array. And finally, when do MIP solvers not typically restart? Yes. Okay. Thank you so much for bearing with me.